All right. So what do I want to do today? I want to start talking about games. So far, we've been talking about learning, and like supposedly this class is about learning and games, so we should get to games. But before we do that, just because it's going to be relevant, last time I gestured a little bit at the fact that online linear optimization algorithms, which are the thing we've been studying up until now, sort of are generically online convex optimization algorithms. And I drew a picture on the board, like a curve, and I drew a line under it, and I kind of wave my hands at it. I want to just cover that, like treat that reduction a little bit more formally first, just because it's going to be relevant to the kinds of applications to games that I want to talk about. Okay, so and just to sort of recap briefly, everything we've done so far has been giving algorithms that have regret guarantees for the online linear optimization problem. Okay, we sort of introduced this formally for the first time when we talked about follow the perturbed leader, but like in hindsight, multiplicative weights was also operating in the online linear optimization setting. And roughly speaking, or not so roughly speaking, even in online linear optimization, the action space of the learner is some d-dimensional vector space. You play a vector. The action space of the adversary is also a d-dimensional vector space, like a cost vector. And then the cost of the learner is the inner product between their action, which is a vector, and the cost vector, which is also a vector. You take the inner product of these two vectors, you get a number, and everything's linear. That's why it's called online linear optimization. We covered multiplicative weights before we defined online linear optimization, but in hindsight, it's just optimizing over the probability simplex. So the vector you choose is a distribution over the k experts. The costs for each expert can also be represented as a vector, and the expected cost of the algorithm is just these inner products. So it's an online linear optimization algorithm. We've seen 3 algorithms for this problem so far: multiplicative weights, follow the perturbed leader, and online gradient descent, and more generally, the family of follow the regularized leader algorithms. Okay. So not everything is linear, and there's this seemingly more general problem called online convex optimization, where every day what the adversary chooses is not a vector of losses, but rather an arbitrary convex loss function. And your loss is this function evaluated on your action. Okay, so it's a generalization in that the loss function need not be linear, it can be convex. Okay. Now the claim, this thing that I want to work through in maybe the first 20 minutes of the class, is that even though this seems more general, we don't need to derive any new algorithms. Like, basically, there's a way to use online linear optimization, this problem that we have derived, at least 3 algorithms for already to solve the online convex optimization problem. Okay, so like we already know how to solve this. Okay, so just to make ideas a little bit more precise, let's remember a couple of things. Like, first of all, what is a convex function? So a function f that takes as input, let's say, a d-dimensional vector and outputs a number is convex if for any 2 points in its domain, for all x1 and x2 in its domain, and for any sort of degree to which I want to mix these 2 components together. So for any mixing weight, say, a number between 0 and 1, it should be that if I evaluate the function on the mixture of these 2 points, on alpha x1 plus 1 minus alpha x2, that this is only smaller than if I first evaluate the function at x1 and x2 and then mix the 2 values in exactly the same way. So it should only be smaller than alpha times f of x1 plus 1 minus alpha times f of x2. Okay, so if I have, like a function that looks like this, right? What does it mean to evaluate the function at 2 points? and then sort of mix between them, it's sort of, what I get is the linear interpolation between those two function values. And what this is saying is that this linear interpolation should live above the curve. If I instead, at any mixture weight, took the same mixture of those points and then evaluated the function at those points, I would get something only below the line. Okay, so that's convexity. Yeah, and so like linear functions are the special case of convex functions where this holds with equality, right? For linear functions, it doesn't matter whether you take the mixture inside of the function argument or outside of the function argument. Okay, so convex functions are nice for all sorts of reasons. Like you've probably come across them in like optimization, like if you want to find the minimum or maximum of a function, like setting the gradient equal to 0 is a good thing to do if it's convex. But actually, like, convex functions don't need to be differentiable, right? Like this thing's a convex function, but there's no gradient. There's no derivative at this sort of sharp point at the bottom. So we might want to talk about subgradients. But first, before we talk about subgradients, let me just talk about some nice like regularity property of a function that'll be nice to be able to assume, which is that I'd really like my functions to be continuous, but not just continuous, but sort of Lipschitz continuous, which means that, so continuity means that, if I want to make sure my function doesn't increase by more than some epsilon amount, there exists some, delta amount such that if I wiggle the input to the function by at most this delta, then I don't change the output by more than epsilon. But if I want to have those like epsilons and deltas like uniformly bounded, then what I want is something that's called Lipschitz continuity. Basically, there should be some, fix, like if I wiggle the input to my function by only some epsilon, then it shouldn't be some arbitrary delta that bounds how much the output of my function deviates, but it should be just uniformly some multiple of epsilon. Okay, so that's called Lipschitz continuity. So a function f is, let's say, L Lipschitz, or L Lipschitz continuous. And you could define this in various norms. I'm going to define this in the L1 norm. But when we've got vectors, the question is, what does it mean to wiggle the input by epsilon? You have to measure that in some norm. The way I'm going to choose to measure it is in the L1 norm, which is just measuring the sum of the absolute values of the wiggles in each coordinate. Okay, so we'll say that a function is L Lipschitz in the L1 norm if, for all pairs of inputs, when I look at how much the function value differs on these two inputs, I can be assured that it is never more than L times the distance between the inputs in like parameter space as measured by the L1 norm. Okay, so it means, like if I wiggle the input by any epsilon in parameter space, the output of the function doesn't change by more than L epsilon. Okay, so a Lipschitz continuous function is always continuous, but it's sort of a uniform notion of sort of continuity with a parameter that we get to talk about. The L1 norm is, like Manhattan distance. So like sum up over all of the coordinates of the absolute value of that coordinate. And then L2 norm is Euclidean distance. And in general, you can have LP norms for any P. Okay. All right, how about subgradients? So fix a convex function again from r to the d to r. A vector c in r to the d is a subgradient of f at a point x if for all x prime, when I look at f of x prime minus f of x, I can be assured that this is always greater than sort of the linear function, which is the inner product of c and x prime minus x. Okay, so if your function is differentiable, a gradient of the function at x is always a subgradient at x, but it makes sense to talk about subgradients even when the function is not differentiable. So for example, this function is not differentiable at its sort of non-differentiable point. It has many subgradients, you know, like this is a subgradient, this is a subgradient, because the function always lies above the linear function. And so, you know, it's just a gradient if your function is differentiable, but we can talk about subgradients even when the function is not differentiable. Okay, makes sense. Okay, and then like a useful fact that I won't prove, but it's not hard to prove, so yes. Okay. Yeah, let's see. I believe the gradient should be if it's differentiable, the gradient should be the unique subgradient, but if someone who knows more analysis than me wants to raise their hand and contradict me at this point, I won't be offended. But I think it's the unique subgradient. Okay. Okay. So like a useful fact, you know, in general, like subgradients could have like really big norm. Okay, like they could have like huge coordinates. And the reduction we're aiming for here, if you sort of remember from last time, reducing online convex optimization to online linear optimization, is that we're going to take these like online linear optimization algorithms, which are expecting to receive cost vectors that, if you remember from our analysis of these algorithms, have to have bounded, you know, costs of bounded magnitude. All of our theorems depended in some way on things like the diameter of the cost space or the maximum value per coordinate. And so if this reduction is going to like work, it had better result in cost vectors of bounded magnitude. But there's nothing saying that subgradients of arbitrary convex functions have to have bounded magnitude. And so the fact that's going to be useful for us in talking about this is that a convex function f is L Lipschitz in the L1 norm. If and only if for every x in its domain, and for every subgradient c of f at x, if I look at the infinity norm of c, which is just a fancy way of saying the maximum absolute value of any coordinate of c, then this is at most L. Okay, so somehow like if I have a subgradient of a function that has really big coordinates, that means that there's a way to change the input by just a little bit in the direction of the large coordinates of the subgradient that will cause the output of the function to change by a lot. And so if I have the promise that the output of the function doesn't change by a lot, if I wiggle the input by only a little bit, that means that the subgradient also can't have any giant coordinates. Okay, so this is why, this is sort of why it's going to be useful for us to talk about sort of the Lipschitz constant of convex functions. It's because in the reduction we're about to see, where we sort of reduce convex optimization to linear optimization, the linear optimization algorithms are going to care about the magnitude of the costs that we feed to them. And the magnitude of those costs, because they're going to be, derived from, or they're going to be subgradients of the convex function, will be controlled by the Lipschitz continuity of these functions. Okay? Yeah. Okay, let's see. I can press buttons. Okay. Did I do it? Or which lights? Okay. There's buttons over there too. Let's see. Oh, no, that's just a flicker. Did I? Is that good? Okay. I mean, it was flickering, so it was already sometimes off. Yeah. Okay, excellent question. Yes.
It's not like obvious because I don't think directly differentiate between convexity and
Let's see. So it's so obvious I didn't bother to prove it. So, but I think it's sort of because like, if you take like a first order Taylor expansion, like the linear term in the Taylor expansion will be a very good approximation to the function within a small epsilon ball. And so the linear, like the first order term in the Taylor expansion will look something like this. And so if there's a large coordinate, you'll be able to like take a step in the direction of that large coordinate, and at least very locally, you will increase, or you'll change the value of the function in proportion to the norm of the gradient. So you may be assuming some like regularity conditions, but again, please contradict me, those of you who know more calculus. I think this is just the fact that gradients are good approximations to functions in like little local balls, assuming appropriate, incantations involving continuity and stuff. Anyways, it's true. Oh yeah, I guess if it's not convex, like it doesn't necessarily make sense to talk about a subgradient. That's right. We could still talk about like a gradient. Yeah, anyways, I'm pretty sure it's like an easy thing to show, but like as a result of not wanting to show it, I haven't thought very hard about it. I'm like quite sure it's true though. Yes. That's right. Yeah, it's hard for me to draw in high dimensions, so I've drawn a one-dimensional function there. Yeah, I mean the subgradient is, going to be like a line in two-dimensional space in that case. Yeah, I guess it's just the slope of the line. But in general, you can talk about subgradients in higher dimensional space. I just can't draw them on the board as easily. Okay, good questions. Other questions? Okay. So what is online convex optimization? Well, it's a lot like online linear optimization. Okay, so there's going to be a parameter L here. I'm gonna define this in which I'm going to define a problem in which the adversary is going to choose at every round an L Lipschitz convex function. So L is implicitly a parameter of the problem. So the learner has some convex action space A, which is a subset of R to the D. The adversary has an action space C consisting of all L Lipschitz convex functions. And then in rounds, just as before, at round T, the learner chooses an action AT from their action space. The adversary chooses a loss function LT, which must be an L Lipschitz convex function. And the learner experiences loss CTL, which is just the evaluation of the convex function chosen by the adversary at the action chosen by the learner. And we can talk about regret just as before. The regret on some transcript that the learner has to an action A is just the sum over all of the rounds of the loss actually experienced by the learner minus the loss that would have been experienced by the learner at the same loss function had they played the same action A every round. Okay, so online linear optimization is just the special case of online convex optimization where, in fact, the adversary is choosing a linear function at each round. This is the generalization where they don't have to choose a linear function. They can choose a convex function, so long as it is Lipschitz. Does this make sense? Yes, good. So note here, right, so this is maybe like a good running opportunity for confusion that we should clear up, right? So, what I emphasized early on is that like it's sort of important that the adversary not be able to see the random coins of the learner, like in the experts problem. Like the learner can, the adversary might know that the learner is going to randomize uniformly between rock and paper and scissors, but they'd better not know that the learner is going to play rock. Okay. How does that show up here, where seemingly there's no randomness, the adversary knows everything? Well, it's that we've assumed the learner has a convex action space. If the learner's action space is rock and paper and scissors, that is not convex, it's a discrete action space. If we wanted to play it in this setting, if we wanted to embed this in this setting, we'd have to say the convex action space of the learner is the set of all probability distributions over rock and paper and scissors, the sort of simplex, in which case the action that the learner would choose at this moment would not be rock or paper or scissors, but rather a probability distribution over them. Okay, so basically, if you have a discrete action space, then the thing that randomization does for you is it convexifies the action space. In general, you can do online linear or online convex optimization without randomness in a convex action space, right? So like online gradient descent, for example, is not a randomized algorithm. even multiplicative weights is not a randomized algorithm if you think of it as playing the distribution, deterministically playing the distribution defined by the weights at every round, right? So no regret learning in general does not require randomness if you're optimizing over a convex action space. The role of randomness is to make your action space convex when it's not already convex. Mm-hmm.
What happens if the number of non-convex?
Among other things, oh, let's see, what happens if your action space? Okay, so let's see. So what's gonna break in our various analyses? Yeah, let's see. I mean, so like it's definitely important that the action space is convex. So if we go back to the analyses of any of our algorithms, gradient descent, multiplicative weights, follow the perturbed leader, convexity is gonna be important. So I'm trying to think of. Yeah. Yeah, so like maybe like concretely, like suppose you're playing online gradient descent, say. Okay, we didn't quite talk about this for arbitrary convex sets, but the way it would work is you would take a step in the direction of the gradient. This might take you generically outside of your action space. And what you're going to do then is project the point back into the action space. Find the point within the action space that is closest in Euclidean norm to this, illegal point you got to by stepping outside of it. And projections work well in convex spaces. You're only going to get closer to any point in the action space, in particular, whatever you want to compare yourself to against at the end when you project back into a convex space, but not necessarily if the space is non-convex. Maybe that's some intuition. Yeah. What kind of space?
The boundary phases of the simplex yeah. We can never say like, but you can say like three over two actions. That would be and now the adversary can like really screw over because they know which space will be playing some. They pick like what can pick something that really should be take the one action that you don't have access to.
Yeah. That's a good example. Okay, good. The convexity is important. Other questions? Okay. Okay, so we have like a bunch of algorithms for online linear optimization, but now we've got this like, oh, yeah. Let's see. Can that happen for convex action spaces? I'm not sure I understand the question. So I think if you have a convex action space and you're doing an L2 projection, you won't run into this issue. There will be a unique closest point. Mm-hmm.
You might have a non-convex and then even if it's not unique as well, and there's still be the last
yeah. So let's see. So I mean, all happy families are alike. Every unhappy family is unhappy in its own way. Like there's lots of, like there's one way to be convex. There's lots of ways to not be convex. The claim is not that there's no way to get sort of regret guarantees in any non-convex problem. The claim is that in every convex problem you can, and if you throw away convexity, then you would need some other property. Okay, good questions. Okay, so we have all these online linear optimization algorithms, but you know, here's an online convex optimization problem. What do we do? So what we do is we give a reduction to online linear optimization. So suppose we have as given an online linear optimization algorithm. Okay, so suppose we're given an algorithm that I'll call LL for linear learn for d-dimensional online linear optimization. Okay, so this could be multiplicative weights, it could be follow the perturbed leader, it could be gradient descent. It's just some algorithm that takes as input cost vectors, d-dimensional cost vectors, every round, produces every round a d-dimensional vector of actions, and guarantees that as measured with respect to these linear losses, it has no regret or diminishing regret to any action in its domain. Okay, so we've seen a bunch of algorithms that have this guarantee. So let's pick one, like online gradient descent, for example. Okay, so what do we do? Well, in rounds, we need to pick an action. Well, we've got this linear learner around that has, it's going to suggest an action. So why don't we play that action? Okay, so from the linear learner, obtain action AT. Okay, so we did our part. We picked an action. Now the adversary is going to give us a loss function. So let's learn what it is. From the adversary, obtain an L Lipschitz convex loss LT. Okay. Now we need to figure out what to feed to the linear learner. The linear learner provided us with an action, but it's expecting to receive like a vector of length d in response, so we got to come up with one. So let's let CT be a vector in which every coordinate is between, let's say, 0 and L, or maybe even minus L and L to the D. Now let's let this be a subgradient of the loss at AT. Okay, so if it's a differentiable loss function, this is just the gradient. Otherwise, any subgradient will suffice. And that's what we're going to feed to the linear learner. So feed CT to the linear learner. Okay, so that's it. Okay, is the algorithm clear? Like the reason that we know that the cost vector is going to be bounded between, have coordinates bounded between minus L and L is because the cost function is assumed to be Lipschitz, and subgradients of Lipschitz cost functions have bounded coordinates. Okay, yep. L is a scalar, and C is a d-dimensional vector whose coordinates are between minus L and L. L is like 5 or something. I don't know if there's also a confusion that our algorithm is called LL. No. Does this make sense? You need to compute a subgradient. That's right. So if it's, yeah, so if it's a differentiable function, you could compute the gradient. But yeah, one of the computational steps in this reduction is computing a subgradient of this function. That's right. Like if you want, this is a reduction that has two computational primitives. One is a way to get no regret for online linear optimization problems, and the other way is a method for getting subgradients for your function. Yeah. Yeah, yeah, like details of auto differentiation are beyond the scope of this course. Like you're just going to assume you can get subgradients. Yes, good question though, that perhaps, easier said than done.
What is that?
Oh, well, this like online linear optimization algorithm, right? It has a certain input-output behavior, right? Like how does online linear optimization work? You choose an action every round, then you receive a cost vector. So C is the cost vector that the algorithm receives. Yeah, so for example, this linear optimization algorithm could be multiplicative weights, could be online gradient descent, it could be follow the perturbed leader. They all have the same sort of API, basically. They give us vectors and then they receive vectors as feedback. So I don't care what the internal workings of this linear optimization algorithm is.
So
Linear learner. That's right. Like you give me a little subroutine for online linear optimization. I use that as a subroutine to give you online convex optimization. Okay. But this makes our naming, for example, of online gradient descent somewhat more justified. It means you can run that algorithm in general with gradients of loss functions. Yep.
This turns any convex loss function into a linear.
The gradient is linear. Yeah.
So,
well, we need to make, like, I haven't claimed what are the properties of this reduction, but certainly it is generating some online linear optimization problem for the linear learner because we're giving it a linear cost vector at every round. Like we're going to need to reason about why this will get a regret bound in the online convex optimization setting. We haven't done that yet, but we have presented our linear learner with some problem of the correct form. We've given it cost vectors every day.
I guess the point of this is that
that's right. So the adversary gives us a convex function. It's not necessarily linear. We compute the subgradient of this thing, which is just a vector, and that's what we feed to the learner. Right. So it's like at this level, it's like a syntactic transformation. The object we got from the adversary was not a vector, it was a convex function. We have, through some machinations, come up with a vector and we're feeding it to the learner. And it remains to be seen whether this was a good idea or not, but like at least this compiles, like, like the subroutine is like, getting the input it needs, right? Yes. I don't know if there's much intuition beyond what we're going to see in a moment in the proof. The proof's going to be very direct. Like, essentially, I mean, why is this going to work? We've got a convex loss function. You've played some point at. The gradient, the subgradient at at, or the gradient at at is going to be like a line tangent to the point that you played. So it's going to have the same loss as the function at the point you played, and everywhere else we'll lower bound it. You're going to guarantee, the online linear learner is going to guarantee that you have loss no more than the best point as evaluated on these linear functions, and that's only less than the loss of the convex functions because the linear function lies below the convex function. This is convexity of the loss function, which is distinct from convexity of the action space. But yeah, convexity is going to be very important for like this thing to work. Make sense? Okay, so like basically this picture is the proof, but let me like write the proof also in equations. Well, first, what is the claim? What's the statement? Okay, so suppose that our little subroutine linear learn is an online linear optimization algorithm that obtains regret to each action A in its action space, bounded by some function R of t after t rounds. For all sequences of cost functions C1 through Ct, where these are vectors that lie in minus L to the D. Okay, so like let's suppose that the object we have is the kind of object we want, an online linear optimization algorithm that has a regret guarantee. In the online linear optimization setting, it will obtain cumulative cost competitive with the best fixed action in hindsight, so long as the cost vectors are bounded. Okay, this is not a mythological object. We've so far in this class been studying like many objects that have exactly this property. Okay. Then, like this algorithm over here, then our reduction obtains regret R of t as well to each of these actions. Okay, so no loss. Like if you have a regret bound that holds for linear functions bounded between minus L and L, then exactly the same regret bound holds for arbitrary convex loss functions so long as they're L Lipschitz. Okay, that's the claim. Same exact bound, yes. That's right. So like the different algorithms we've seen so far each will have some dependence, that the dependence is different for the different algorithms on L. In general, yeah, like the scale of the cost is important. Multiplicative weights has some dependence, gradient descent has some dependence, follow the perturbed leader has some dependence. So I'm just not worrying about the specifics of the algorithm. But it's important that all of those algorithms, like otherwise this regret bound would be a function of like t and L. Like all of the algorithms have a dependence that all of the algorithms do have some dependence on L. Yeah.
I think it makes sense now why it happened. Because how many functions have a local only one for if it's not convex, it's really
Oh, for sure, the functions have to be convex. I think the question from before is why does the action space have to be convex? Which it also has to be, but yeah, like certainly the function has to be convex. Like otherwise the subgradient's not even defined. Yeah. Linear function is the worst case, yeah. So that's sort of the spirit of this. Like your regret bounds, like we're gonna pretend everything's linear by getting the best local linear approximation, the gradient. And the proof is, the theorem and the proof are gonna sort of say linear is the worst case. If the function is nonlinear, if it sometimes lies above the gradient, then Yeah, that only helps the regret bound. Yes. Yeah, it's like somehow like actual convexity is going to help you. We'll see that in the proof. Okay. All right, so let's basically reproduce this picture, but in math. Okay, so we want to claim that to every action, the regret of our online convex optimization algorithm is the same as the regret for our underlying online linear optimization algorithm. Okay, so fix a comparator A that we want to compare to. Well, let's invoke the guarantee of the online linear optimization algorithm. Okay, the regret of the online linear optimization algorithm is just the sum over all of the time steps of the regret of the algorithm, which as far as it's concerned is just the inner product of AT and CT, right? Like we told it CT was the cost vector. It doesn't know that in the world outside of the matrix, there's this more complicated loss function. As far as it's concerned, this is the loss of the algorithm. And its regret to a fixed action similarly is evaluated by taking the inner product with CT. Now, the whole premise is that for any sequence of cost functions, and in particular the one fed to it by our reduction here, this regret will be bounded by RT. So we know that the regret of the linear learner is at most RT. Okay. Now, this is just, everything's linear here, so this is just the sum over all of the rounds of the inner product of AT minus A CT. Okay, I can take the difference inside the inner product because everything's linear. Okay, and now we're going to use the fact that CT is a subgradient of this function. Okay, like what was the definition of a subgradient? It was that this quantity, term by term, is only bigger than the difference between LT evaluated at AT minus LT evaluated at A. Right, this is just the statement that the function lies above the line. But this is just the actual regret that our reduction has to action A by definition. Okay, so that's it. This, everything here is an equality except this step. This step's also an equality if the functions are linear. So linear is the worst case. If it's convex, you're only doing better. Okay. So everything we know, everything we've done up until this point for online linear optimization, all of it works for online convex optimization. And like, just to note something obvious but useful to keep in mind as we start talking about games, we've been talking about a learner who wants to minimize a convex function. We could have talked about a learner who wants to maximize a concave function just by putting negative signs everywhere. Okay, so you can get no regret for online convex minimization problems, and you can also get no regret for online concave maximization problems, just because the negative of a concave function is a convex function. Okay, makes sense? Yes. Yes, so you can be strongly convex. So, like in the spirit, right? Like, yeah, like in the spirit where things only, you're only helped if you're actually not linear, right? Like, just for regular online convex optimization, you can't hope to get better bounds than for online linear optimization because the problem encompasses online linear optimization. But if I promise you that actually, you know, you're strictly convex, you're definitely going to lie like strictly above this line everywhere, and maybe even more than that, strongly convex, which means you're lower bounded not just by a linear function, but by some quadratic function, then you can take advantage of that to get strictly better bounds than for online linear optimization. That's true. And yeah, maybe there's some intuition here where like you're saving something here if you are strongly convex. Yes. Mm-hmm. Yeah, if the thing wasn't Lipschitz, then the subgradient would have arbitrarily, you know, could in principle have arbitrarily large coordinates, and we just, you know, the proof would still go through, but like we would need a linear learner that had no regret to sequences of cost functions that could be unboundedly large, and we don't have such an object. Like the linear learners we have some dependence on the scale of the problem. So Lipschitzness is important here because boundedness of the cost functions is important for online linear optimization.
Not the same reason why convex action space is important, or is it used somewhere here? Or is it only used
I don't think it's the same reason convex action space is. Well, so the linear learner also needs to have a convex action space. Yes, so like this reduction is not explicitly using that, but the linear learners need a convex action space. Yeah. Exactly, and in fact, you know, like I used L1 norm because it gives you sort of bounded L infinity norm for the costs, which is the thing that you want for something like multiplicative weights. But actually for gradient descent, if you remember, the dependence on the cost is the L2 norm of the cost vector. And so there, to get the tightest bound, you'd want to assume that your functions were Lipschitz in the L2 norm, because the conjugate norm is also L2, and that would give you boundedness of the cost functions in L2. So there's, yeah, so like L1 is sort of the right choice here, only if your linear learner depends on the L infinity norm of the costs, like multiplicative weights. You'd want L2 if it was gradient descent, and more generally, you're right, like you want a conjugate pair of norms. Yeah.
Sorry, I'm questioning this, but I thought because of the inner part of B when X and minus X is less than or equal to F into X and F.
Let's see. So we said a subgradient at X must satisfy for all X prime F of X prime minus F of X greater than or equal to C inner product with X prime minus X. Okay, so let's see. So here, I bet what's happening is that I don't think so. So let's see. So let's just make sure. I'm guessing what's going to happen is we're going to multiply both sides by -1. So this is like C is the subgradient at AT. Okay, whereas here, C is the subgradient at X. So if we want to map this onto here, we need to multiply both sides by -1, which is going to reverse the inequality. Good question, but I think I escaped on that one. Okay. Other questions? Okay. So now I want to talk about games. And I want to start by talking about zero-sum games. Okay, so you've all seen zero-sum games before, like rock, paper, scissors is an example of a zero-sum game, right? Like I've got some collection of actions, rock and paper and scissors, you've got some, and our interests are strictly opposed. I'm going to win, or you're going to win, and if I win, you lose, and vice versa. Okay, that's a two-player zero-sum game. We can define two-player zero-sum games more generally than that. Yeah, so like if you've seen things like von Neumann's min-max theorem, it's usually stated for like matrix games like rock and paper and scissors, and you're allowed to randomize, which gives you like a linear loss function over your linear over your mixed strategies. Because we're going to prove a version of the min-max theorem, but because we have not just online linear optimization algorithms, but online convex minimization and concave maximization algorithms, we will prove a version of the minimax theorem that extends beyond linear losses to convex concave games. Yeah, that was why it's useful to observe these things. Yeah, so let me tell you what zero-sum games are, maybe in somewhat more generality than you've seen them if you took like an undergraduate game theory class, say. So we're gonna have it's a two-player game, and I'm gonna anthropomorphize the players, and they're gonna be named Max and Min, and Max wants to maximize something, and Min wants to minimize something. Okay. So a zero-sum game, strictly speaking, a two-player zero-sum game, but for reasons we can talk about, zero-sum games, zero-sum structure is not very interesting if there's more than two players. It doesn't impose many constraints on the game. A zero-sum game is defined by a maximization player with a closed bounded action set, which I'll call A max, and I'll assume is embedded somehow in R to the D, so it's a subset of vectors. A minimization player who also has a closed bounded action set, which I'll call A min, and I'll assume is a subset of, I guess if it's closed, it can't be equal to, so a strict subset of R to the, let's say this one's R to the M, and this one's R to the N. So they don't have to be the same dimension, say. And some bounded utility function. Which I'll call U, and takes as input an action from the maximization player and an action for the minimization player, and outputs, let's say, a number in some bounded range between 0 and B. Yeah. They will have to be convex if we want the minimax theorem to hold, but at this point, who knows what the minimax theorem even is? But just but yes, like to like foreshadow a bit, for the minimax theorem to hold, we're going to want both of the action spaces to additionally be convex. We're going to want the utility function to be convex in the minimization player's action and concave in the maximization player's action. These the restrictions we will put on the game in order for the minimax theorem to hold will, for a pretty fundamental reason, correspond exactly to the restrictions we need in order for there to be online learning algorithms. Yeah. Sure. But up to scaling, it doesn't really matter, right? Like if I don't like negative numbers, I can, suppose they go from negative b to b, then I could just add b to the utility for everything, and now it would go from like 0 to 2b, and I wouldn't have changed any strategic aspect of the game. Then yeah, like there's nothing here that sums to 0. It's just, something that is, someone wants to minimize it and someone wants to maximize it. So, yeah, that's right. Like okay, good point. Like, why are these called zero-sum games? Right? There's no 0 that shows up here. Like, what's going on? The reason is because, in general, in a game, both players would have some utility function. And a zero-sum, one way to define a zero-sum game is one in which at every pair of actions, the sum of the utility functions of the two players is 0. Okay, but it's sort of silly to talk, if that's the case, it's sort of silly to talk about two different utility functions. I could just say, okay, well, since Max's utility is the negative of Min's utility, I could just say Max wants to maximize his utility and Min wants to minimize Max's utility. And now, this captures all constant sum games. The 0 was never important. Like, instead of talking about zero-sum games, you could talk about 5-sum games. So all these games are the same up to some shift. Good. Other questions? The point is just that, like, these are games in which the players are strictly opposed to one another. What's good for one is bad for the other, and vice versa.
And when you have both vectors, what's good for one is bad for all of it.
Yeah, so these are just two-player zero-sum games. You could define multiplayer zero-sum games in various ways, like the sum of their utilities is always 0 would be a natural way to do it. But generally, that's not an interesting set of games, because suppose you give me your favorite, most complicated, n-person game that you can think of. I'm going to define a strategically equivalent n+1 person game in which I introduce a dummy player who's has no strategic effect on the game. His actions don't affect the utility of any of the other players. But his utility is just defined to be at every action profile the negative of the sum of the utilities of all the other players. So now this is a zero-sum game by fiat, because I just introduced this like additional player who, his only job is to have utility opposite that of the sum of everyone else. So everything sums to 0. But he actually has no effect on like the equilibrium structure of the game, because he's payoff irrelevant to the other players. And so if you were hoping that zero-sum games would have some special properties, which for 2 players they do, for n players you're going to be disappointed, because now I've given you an n+1 player game that is zero-sum, that has all of the pathologies of whatever arbitrary n-player game you gave me.
I didn't mean that I have to 0. I was talking about when it was when what if you are zero like something has like usually something that's one and one
Let's see. I'm going to say something that I'm not sure is directly answering your question, but there are ways to define multiplayer games that share some of the structure of 2-player zero-sum games by restricting which players are payoff relevant to which others. So, for example, I could define a game where the interactions are separable, meaning everyone in this room chooses an action. But to figure out my utility, I figure out pairwise my utility with each other player, and then add those up. Okay. Separable games like that, if they happen also to be zero-sum, share lots of the nice properties of zero-sum 2-player games. But the separableness is important.
Yeah, I'm just trying to...
Yeah. Well, none of this comes in for the definition. There's only 2 players in the definition, right? This is a 2-player game, a minimization player and a maximization player. But yeah, like if you wanted to generalize it to multiple players, you'd need some additional structure. Okay, good. Other questions? Okay. Okay, so like as their names suggest, like Max would like to play so as to make the number that comes out of this function big, and Min would like to play so as to make the number that comes out of this function small. And a priori, like it's not clear how they should do that. Like, if they're both if it's like rock, paper, scissors, and they both have to pick an action at the same time, like what should they do? Like, what number comes out of this depends not just on your action, but on the action of your opponent, and you don't know what your opponent's action is going to be yet. So it's not clear a priori how you should decide to act in a zero-sum game. It would be much easier to figure out what to do if your opponent told you ahead of time what they were going to do. Right? If your opponent, say you're Max, then Min tells you, right? The problem here is, the thing you care about is the output of a 2-argument function, and you only control one of those arguments. But suppose you're Max and Min tells you what they're going to do. So now you know what goes into like Min's argument in this function. What comes out of this function is now entirely under your control. It's what, a function only of your own action. You're Max, so you want the number that comes out to be big. And so what you should do is you should, in this 1-argument function whose argument is under your control, you should like plug in the action that causes the number to be as big as possible. Okay, that's called your best response. And Min has something similar. If Min knew what Max was going to do, she would be in control of a 1-argument function that she wanted to minimize. She would just choose her action to minimize it. We could call that her best response. Okay. So, the set of best responses for Max, given an action A2 for Min, is, and I'll write this as BR for best response sub Max. It's a function of A2. Okay, what are the things that Max should do if he knew that Min was going to play A2? Well, it's the set of actions that maximize amongst all of his actions the utility that he wants to maximize when Min plays A2. Similarly, I can talk about Min's set of best responses. Okay, the best responses for Min, if Max plays A1, these are just the actions in Min's action space that happen to minimize the utility function when Max plays A1. Okay, so like not clear how to play a simultaneous move game because the thing you care about is a function not just of what you do, but what your opponents do. But if you're the only player, it's clear what to do, like just maximize the function. And so you would be put into this easy position of being able to figure out what to do if your opponent was kind enough to like give the game away and tell you ahead of time what they were going to do. Okay, and that function that sort of tells you what to do as a function of what your opponent is doing, that's the best response function. Does that make sense? Okay, by the way, like, I haven't said convex yet because we haven't proven the minimax theorem. I did say closed and bounded. How come? Well, I want the, that means the best responses are well defined. Like in general, we can't even talk about best responses if I can't take maxes over these sets. But at least, if I have closed and bounded action spaces, then I can talk about best responses. Okay. So how should we think about simultaneous move play? Right, so best responses are sort of about sequential play, right? Like, you know, your opponent tells you what to do, what they're going to do, only then do you make your decision. In simultaneous move play, you can at least figure out if you regret what you did in hindsight, now that you know what your opponent did. Okay, like, you know, I choose an action, Max chooses an action, Min chooses an action. They do so without knowledge of each other's choices, but, you know, like, then they learn what each other's actions are. We can ask if like they're sad about what they did, if they regret not having done something else. Okay. So maybe one way to think about this is that if Max is sorry about how things turned out, then we're not in a stable point in the game because maybe tomorrow he's going to do something else. Similarly, if Min is sorry about how things turned out, maybe tomorrow she's going to change her behavior. But if we're both like pretty happy with our, you know, the actions we chose, given what our opponent did, then maybe we're at a stable point in the game and we'll keep doing it. Okay, and so this is the idea behind Nash equilibrium, sort of a way of defining stable points in strategic interactions. So a Nash equilibrium is just a pair of actions such that both of the players are playing best responses to what their opponents are doing. Right? If we both choose something and then I find I could have done better given what you did, we're not at equilibrium. But if we both choose actions and then I find, what I did actually was a best response to what you did, and similarly you find that what you did was a best response to what I did, then neither of us can make any improvements unilaterally. Yeah. It is still regret to a single action. Is there any other action you could have played which would have given higher utility given what your opponent did? Let me write it down and then we can. Okay, so a pair of actions, A1 and A2, one for Max and one for Min, is a Nash equilibrium if both A1 is a best response for Max to A2, and also A2 is a best response to Min, for Min, to A1. Okay, so it's still a notion of sort of, you know, there's no repeated thing here, but it's still a notion of regret to a single action. We're asking, given what actually happened, that you played A1 and A2, could you, as Max, have done better by playing something else, A1 prime, by playing some other action? If the answer is yes, you've got regret to that other action, then you're not playing a best response, and it's not a Nash equilibrium. But if the answer is no, you're actually playing the best action you could, given what your opponent did. And if the same is true for Min, then that is a Nash equilibrium. Does that make sense? Okay, so, you know, like a set of stable states here, you know, stable in the sense of Nash equilibria are just a pair of actions such that both of them are simultaneously a best response to the other, sort of a fixed point of this best response correspondence. Best response generally tells you, given what your opponent does, what should you have done instead? So you can think of it as, you know, mapping game states to other ones, you know, as people try to like unilaterally improve. This is like a fixed point of that mapping where neither player can improve. Like the best response correspondence points to where you already are. Yeah. So far I've just like defined these things, but like, yeah, you might ask like, when do Nash equilibria exist, even in zero-sum games? I haven't, for example, required in the definition yet that the action sets be convex. So like in rock, I could encode a game where like you have 3 discrete actions, rock and paper and scissors. And in such a game, there would be no Nash equilibrium the way I've defined it, because how can if I play rock and you play scissors, like one of us won and the other lost, and we can't both be happy about what happened. So, right. So like in general, these things don't exist, right? Like how, in rock, paper, scissors, if I'm not allowed to randomize, there's not going to be a fixed point like this. Now, so a natural question is, when are these things going to exist? And a consequence of what we're going to prove next is that it is sufficient that the action spaces are convex and that the utility function be convex concave. But that's not like a priori obvious. Like, yeah, but like I can define this thing, but like, why should fixed points like this even exist? Yeah.
In your rock paper scissors example, A1 isn't just wrong. It's like 33% wrong.
If I define the game in that way, where my set of actions was the set of probability distributions over rock and paper and scissors, then yes, the Nash equilibrium, there would be a Nash equilibrium of this game, and the equilibrium strategies would be that each of us would uniformly randomly randomize between rock and paper and scissors. But if I defined the game as I could have so far, since I haven't specified convexity of the action spaces, as there being exactly 3 actions, rock and paper and scissors, then Nash equilibrium would not exist. Yeah, so like this is a good example to like note that if we want the existence, like it's not obvious that these things should exist. In fact, in the like generality in which I've defined the problem so far, they don't. Like rock, paper, scissors with deterministic strategies is a good example. Yeah, what we're going to prove is that basically convexity is enough to guarantee existence, and that's why randomization is useful. Randomization convexifies discrete spaces. Yeah. Yeah, that's right. So in general, for the existence of Nash equilibria, not just in 2-player games, but in n-player games, you don't need convexity. You just need, or you don't need convexity of the utility function. You just need continuity. And in general, you'd prove these with, a fixed point theorem. And you'd get something, like the equilibria wouldn't necessarily have nice structure. They wouldn't necessarily be easy to find. Fixed point theorems sort of don't give you any of that. Zero-sum games are special, and we're not going to need a fixed point theorem. We're going to prove the existence of equilibria at the same time that we prove structure about them, the minimax theorem, without needing to know any fixed point theorems, only needing to know about ultimately multiplicative weights, online linear optimization, which is also online convex optimization. Okay. Everything makes sense so far? Okay. All right. So, okay, so like Nash equilibrium, we can define a stable state like this, but this doesn't give much guidance for like how to play. Like, like how do I find a Nash equilibrium, for example? Or, like, do they even exist? And so, and so somehow the difficulty in thinking about this is because of the nature of simultaneous move play. I have to commit to what I'm going to do before I know what my opponent is going to do. It's a lot easier to think about sequential play. Okay, suppose I'm Max. And what I need to do is I need to fix a strategy, fix an action, and then tell it to Min. So I go first in like a sequential game. Then min will get to think about the action I just told her I was going to play, and only then choose her action. Okay. In a game like that, it's more straightforward to think about how I should go about playing. Okay, because I know what min's going to do, right? I have a choice for which action I'm going to play. But once I commit to my action, what min is going to do is she's just going to best respond. There's no reason for her to do anything other than best respond. There's no further interaction with me, right? Like once I commit to what I'm going to do, min is going to play a best response. So what should I do? I should, so now if I sort of think about this at one step of removal, for every action I could play, I know what min is going to do. She's going to best respond. And therefore, I know the utility that will result. It will result, it's from plugging in my own action to the utility function together with min's best response to my action. So what I should do is I should play the action that will maximize the utility that I get after min best responds. Okay. Similarly, how should min play if she's forced to go first? She should, she knows what I'm going to do. I'm max. She knows that I'm going to best respond to her action. I'm going to choose the thing that maximizes the utility given what she chose. And so knowing this, she should choose the action that minimizes the utility that will result after I best respond to that action. Okay. So the strategies that result from this kind of sequential reasoning are called maxi-min and mini-max strategies, because they result from iteratively thinking about maximizing a minimum or minimizing a maximum. We'll say that A1 is a maxi-min strategy for max if A1 maximizes among all of Max's strategies the utility that he gets after min has an opportunity to best respond and choose her action to minimize the utility of A1 and A2. Okay, so a maxi-min strategy is what Max should play if he has to go first and announce his action to min. Because once he announces his action A to min, what she's going to do is she's going to best respond. She's going to choose the action that minimizes the resulting utility. And therefore, Max should choose A to maximize the utility after min's minimization. Okay, so min's going to minimize, Max is going to maximize. He's going first. He wants to solve this outer maximization problem. It's a nested max-min problem. Okay, so this is what Max should do if he is going first. That's called a maxi-min strategy. And similarly, what should min do? Well, she should play a mini-max strategy. So A2 is a mini-max strategy for min if A2 is a minimizer in the argmin amongst all of min's actions of the function that maximizes amongst all of Max's actions the utility that is obtained when Max plays A1 and min plays A. So it's exactly the result of strategic reasoning, but the other way around. What should Min have to do? What should Min do if she has to go first and commit to an action, knowing that Max is going to go second and best respond? Okay. In general, it's simultaneous move play. It's not clear like what you should do because you don't know what your opponent's going to do. But in sequential move play, you do know what your opponent's going to do. If you've modeled their incentives correctly, they're going to maximize or minimize their utility. So it's easy to think about how to play in sequential play in a zero-sum game. Okay. Now these are the maxi-min and mini-max strategies. They're actions for max and min. We can also talk about the maxi-min and mini-max values of the game. What is the utility function if max goes first and min best responds? What is the value of the utility? Or the mini-max value of the game? What is the value of the utility function that comes out of this min-max optimization if min goes first and max best responds? Okay. In general, it would seem that it is a disadvantage to go first. You're revealing information about what you're going to do to your opponent, giving them more information to optimize against you without limiting their strategy space in any way. Why would you want to do that? But the theorem we're going to prove next class is that if we add some convexity assumptions to the structure of the zero-sum game, these are going to be, for reasons that are not a coincidence, exactly the assumptions that are needed for us to have online convex optimization algorithms with regret bounds. Then in fact, we will show one, that it doesn't matter who goes first. The maxi-min value of the game is equal to the mini-max value of the game. And two, that Nash equilibria strategies have to be pairs of maxi-min and mini-max strategies, respectively. So in fact, figuring out how to act in the simultaneous move game is no more complicated than figuring out how to act in the sequential move game. The sort of, and the moral of the story is going to be, whenever you can run no regret algorithms in a game, the order of play does not matter. You could go first, you go second, you could move simultaneously, doesn't matter. It's all going to come out the same way. Okay, and there's going to be a deep connection between the existence of no regret algorithms and the existence of minimax theorems. Essentially, whenever we have no regret algorithms, we can prove a minimax theorem, and directly from minimax theorems, we can derive no regret algorithms. So there's a sense in which these no regret, the online convex optimization algorithms we've been studying that have guarantees for adversarial sequences, these are constructive versions of minimax theorems in a very strong sense. Okay, so we'll dive into that next time. Oh, yes. Exactly. And I gain, there's no disadvantage for me telling you what I'm going to do. I can say, guess what? I'm going to play rock a third of the time, paper a third of the time, scissors a third of the time. That doesn't help you. That's true not just of rock, paper, scissors, but of all zero-sum games, which turns out to be like an important fact about the world. All right, so we'll dive more into that next time.